last lecture I did not actually get all factors correct, and it was kind of deliberate. I want you to go back and work things out. I mean, because the structure is well known and you know the structure constants for instance for the group for the Lie algebra and so forth. So, going back you can work it out, and you have done some of it in your assignments as well. So, I just wanted to emphasize only the structure. Somebody asked me, is there any reference? Actually any book on quantum field theory will have whatever I discussed, and just so I give you a concise reference, this a single reference if you wish, Pierre Ramon's book on quantum field theory. It is I think the fastest introduction to starting calculations in quantum field theory. Does not waste a lot of time on things, and in particular he has everything sort of very concisely in the first 20 pages, all the stuff that you need before you can get started doing quantum field theory. And among other things he does representations of the Lorentz group as well as the Poincare group out there. And just one thing, I think yesterday I said that this should go like m square times s into s plus 1, and I think there is a sign or minus sign in our convention, okay. But that is again something which you can so these are the eigenvalues of this Casimir, should be that, okay. And one more caution is that whenever you look at any book on quantum field theory, first thing you have to do is to probably look at the appendix where they define their conventions. In particular, is the metric convention plus minus 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 or minus plus plus plus, and all these will. So, p mu would be minus mu square in the other convention. So, these are all details, but I think the idea here is that the Poincare group has two Casimirs, which are these two, okay. So, now what I am going to do is discuss go back to discussing classical solutions. So, what we will discuss in the next two lectures is magnetically charged solutions, okay. And I have already given you two assignments on this. One was on the Dirac monopole, and this lecture you could say is related to, and the next one is I would say on the 't Hooft Polyakov monopole, but I do not do it in their version. It is done in a simplified version, which is due to Prasad and Sommerfeld. Okay, this should take us about a couple of lectures. So, it is kind of counterintuitive. We know that we do not see anything which has electrically which carries magnetic charge, okay, and that is really reflected in Maxwell's equations, which we write out as del dot B equal to 0, okay. And this is what actually lets us solve for, we can solve for B in terms of the vector field A, okay. So, and just by analogy we can with electric field, let me put a subscript here E. So, the difference between these two is that there are sources of electric charge while there are no sources of magnetic charge. So, if somebody comes and asks you if there are magnetically charged objects, how would you modify Maxwell's equations? It seems very obvious to write something like a 4 pi rho m out here and call that magnetic charge, okay. But if that is true, then this is not possible if magnetically charged objects or sources exist. And that kind of and we saw that when we did electromagnetism, it was very important for us that we wrote that the basic field there was the vector this combining with the scalar potential to form a 4 vector, and you got this vector field. And it sort of tells you that if you have things which have electric charge as well, of course you could write this thing, but you can see that the Lagrangian description would be in trouble. We cannot write, okay, and the answer to that is that there cannot be, I think, a local description where you have both electric and magnetic charges simultaneously present. And if you think that that is a figment of my imagination, that these things will never happen, at least theoretically speaking, there exist theories which are toy models, but which have limits where the low energy degrees of freedom of those things are both electric and magnetic charge objects. Okay. What we will see in the, for instance, in this, that we will construct magnetically charged objects, but typically they will be very massive. Okay. So if you are looking for low energy degrees of freedom, it is okay, there is no monopoles, you can forget about it and work with this kind of setting and you are okay. So, but we will today we will be assuming something, we will proceed a la Dirac in 1931 or 1930-31, where he actually asked what would be the effect of finding a single magnetically charged object, a point object which carries magnetic charge. Okay. So his idea was, so suppose let us just go back through this, and if you have an electric charge, point electric charge, you would have written the source for that as the charge times a delta function. This would be a, this is like a point charge placed at the origin, and what is the electric field due to this? Or should I put a q here? Okay, I will leave E. Okay. So this is what you would have written, right, 1 upon r square times a unit vector in this thing. We are working in Gaussian units, right. So is there any pi for 4 pi? No, nothing. 1 by 4 pi epsilon naught is 1. So this is what you have. So in exact analysis, so the thing is, one more point is that the source free Maxwell's equations admit a nice symmetry, which is E goes to B and B goes to minus E. Okay. Presence of sources is what messes it up. So if there were no sources, electric sources, this would also be 0. Okay. So we are just talking of free Maxwell's equations, that is d mu f mu nu equal to 0. Okay. And then there is the symmetry. So if you just see that, just using that analogy, you can see that I can always I can write out what would be the magnetic field due to a point magnetic charge just by using this symmetry. Okay. So you could make this a symmetry of the theory even with sources by just saying that I exchange electric and magnetic sources, but there are no magnetic sources. So this just go ahead and write del dot B equal to 4 pi rho m, and del dot E would be 0 in the new thing. That is okay. I am not writing the other two Maxwell's equations, they will also work out. Okay. So using that this thing, Dirac in 1931, he wrote, let us look for a point monopole. So he called the magnetic pole is what he called it those days, but we will call it a monopole. Monopole of charge G located at the origin. So just looking at what we have out here, that would just be B would be G by r square and del dot B would be okay. So the thing is that if you observe here at space is just R3. If we delete the origin, del dot B is 0, because this is a delta function. Okay. So it is not so bad. I mean, we have a point charge, so it is really at every point except every point in space except one point, things are normal. Okay. So this kind of says that so this will naively suggest that we can write A exists everywhere except the origin. This is a naive guess, right? But the important point here is this guess is wrong. Okay, this cannot be true. So why is that? So the analog of Gauss's law again would be integral. Again I will just write out first for, so let us take a 2 sphere of any radius r centered at the origin with some radius r, E dot ds, what would this be? 4 pi times the charge enclosed. Okay. So in analogy with this, we can write integral over any radius S2. So this is a sphere of radius r centered at the origin. Okay. I am just taking, I can choose any Gaussian surface that encloses that charge, then it is okay. So I will get B dot ds should be 4 pi g. Okay. Now the most important point here is, if you look here, this integral is done everywhere where I mean you can see that at no point where this integral is being done, okay, is I mean it is not passing the origin does not intersect any of these points, it is a perfect, it is a sphere away from this thing. Okay. But so we have said, but del dot B is 0. Yeah. Okay. So now the thing is, suppose A and A exists, then I claim that would imply that integral B dot ds equal to 0. So how do we see that? And let us just do in the let me do some draw some pictures here. So let us say that I chose a sphere, and so x, y and z axis, and let us say that I create a hole, okay, of some small radius little a. Okay. So what I have done here is what I have is a sphere with a hole in it. So really I have an open surface. Okay. I can evaluate this, I will evaluate the same integral, it is no longer a closed integral, okay, but it is an integral over S2 of r minus a disk, it is an open integral B dot ds. Okay. This should be equal to okay. But so this is just a flux through this thing, and this we can write this as a line integral over the boundary of this thing. So this is equal to integral of A dot dl, a closed integral where this is the integral over this guy, some orientation will be there. Okay. We won't, I am not worrying that, you can take care of that thing. Okay. Integral of A dot dl. Okay. So, this is equal to the flux over this. So, what is it I wanted to argue? I wanted to argue that yeah, yes. So, this is just over L, and now the idea is that now I just take the radius of the disk. So, this is over a disk of radius a, and in principle if I take the disk to become smaller and smaller, in the limit of a going to 0 we would expect this thing to vanish. Zero as this conflicts what we have just written out here. Okay. So, the only way this can go wrong is if a becomes singular somewhere such that it will cancel, even though so dl is something which is of size a going to this thing, if this goes blows up at some point as by 1 by a, then we can get some cancellation. Okay. So, what it implies is that a will necessarily blow up at least at one point or some small region, it has to blow up, there is no okay. So, even though we said that a exists everywhere, whenever we say mathematically, when we say something it exists, what we mean is that it is non singular, nice smooth function, we can take derivatives, everything works. Okay. That is why I was going through all these I mean all these things assume these things implicitly, we never think of it deeply, but that is the point. So, that has to be violated. Okay. And so what we will see is that the best case scenario is that it will be violated at some point, one point on every sphere. Best case scenario would be this, and so I gave in your assignment I had given you two such choices. First one I write as a vector south, okay. So, let us see where does so first thing is this is well defined everywhere except when this thing blows up, okay, at r equal to 0 and r plus z equal to 0. These are the 2 points it blows up. R equal to 0 is the origin, but we can live with that. That's we said we will delete that point, but this is the guy which is more important, it blows up here. So, this is z equal to minus r. When does this happen? That is, this occurs at the negative z axis, which is x equal to 0, y equal to 0. So, what it says is that, and let me use a red chalk here or a pink, is this pink? Yeah. So, what it says that at every the A I have written is messed up at the south pole, okay. And then you can check. So, what this says is that, so now we can go ahead and if we agree to delete that z axis, we can just blindly go ahead and work out what is del cross A s for r plus z not equal to 0 at all points where r plus z is not equal to 0, and you can check that this is equal to b. B, let us give it, call it M for magnetic monopole. Okay. So, So just following these arguments you will see that it is necessarily, so we will get roughly 0 from all the other guys. So all the flux should really go through this to make the thing work. Okay, so implies, so to make Gauss's law work, we need to have a flux tube of 0 size, if you wish, of 0 thickness along the negative z axis. Okay. This was Dirac's observation. Okay. And since a tube of 0 thing is a string, so this object has a name, it is called a string, a Dirac string. Yes.
You said that all the flux will be along this single string, but we started off with the assumption that we want the magnetic field to be in the radial direction of the 1 by r square profile.
The B, through the B, but we are looking at A. So if you do it through B, so how do I explain this? Okay. So the thing is, yeah, good point. So yeah, so okay, yeah, let's so let's assume that there so the idea here, yeah, that's a good point. And so the reason is that so the computation, there are two computations one is doing. Computation 1 is working with B and carrying out integral B dot ds, no problem with that. Okay. But now if you so what one is doing here is, suppose I go ahead and assume there is an A which works everywhere. Okay. Now that has to give a 0 answer. I can even do something like try to regulate things, so it will mess up. So I could do one thing, which is to regulate this. Okay. If I regulate this, so let me write out an equation and then we will make sense of that. Okay, that is a good point, and this is exactly. So what I am saying is that if you actually are willing to go outside the space of just smooth functions and work with distributions, del cross AS will not satisfy okay. So if you did a flux integration with this guy, so let us say this was true, then this integral should give 0. Okay. So what I am saying is, so there are two contributions to del cross AS. One is it agrees with this everywhere, but along the negative z axis there is this contribution. So if you go ahead and regulate things and do it correctly, what you will see is that you will get something. So let us say we regulate it. So it is no longer it does not, so what will happen is it will not agree with B in that region, okay, and but it will be a perfectly smooth A. So integral of that thing over the closed thing will be 0. So what one is saying here is, this will give a G flux, this contribution of this will be precisely opposite and give 0. Okay. So the Dirac string, if you wish, carries exactly the amount of flux to cancel the other guy. Okay. So but the thing is that what you can do is something much more, this thing is you can look for other solutions. Let us look for we will say something called north, which is more or less the same as this, except it corresponds to changing a few signs here and there. So, this is just the assignment which I have given you people, I am just looking at. So, this has the same property, except that it now blows up at r equal to z or z equal to r, which is a positive z axis. Okay. But now you can see that on regions, if we delete the z axis, full z axis, then these two will give the same a n and a s will give the same b. So, del cross a n will give the same thing with a plus out here. This theta function is just 0, the Heaviside theta function, 0 and 1. Okay. So, theta of x is equal to 0 for x less than 0, 1 for x greater than 0, probably half is what one writes for 0, right. Okay, that is a Heaviside theta function. Okay. So, they will give the same b. So, what does that imply? That a n minus a s should give 0 field and should be gauge equivalent. Of some lambda. Okay, because b is 0, then you use just the usual thing, curl grad is 0 or whatever that identity. So, you can actually, in this assignment I believe I have asked you to actually compute this. Okay. So, what you can see is that if you agree to use two patches in some sense, one for which covers so what it is kind of nice. So, let us focus on just the sphere. What you do is geometrically, so I will just take a projection. So, what we can do is we can choose to cover the sphere by two things. One region is this, deleting the south pole, and the other one is okay. So, if you agree to work with two what do you call, two vector potentials, we actually can work nicely without ever we can cover these things and we can get stuff which goes with this. We can still work with the vector potential. Okay. So, but the question is so, and you can ask, can I write more general solutions? The answer is yes, and you can show that by gauge transformation. So, another way of saying it, so since these two are related by a gauge transformation, and one way of saying it is that the gauge effect of a gauge transformation is to take this Dirac string here and take it from here and rotate it and push it to the north. But it need not do just that, you could write more general gauge transformations and you could get arbitrary line string going away to infinity, which will intersect every sphere of a given radius once. It will still satisfy all these things, except it will be a pain if you give me some curve and ask me to write the thing. I guess I can leave it as a homework assignment for you to work it out. Okay. Given a curve which intersects every sphere once, what is the gauge transformation which will take, say, this string to that. Okay. But it is probably a better thing to do is to just take some arbitrary lambda, put it in and plot the string. Okay, that might be a more sort of a fun exercise. So, this is just a classical exercise, and we see that if you choose to work with one potential, we have to live with a string. So, Dirac did not stop there. I mean, this is nothing, this looks like a homework assignment in Jackson or whatever, where you are regulating these things, and working to show that. I mean, the hard part in this computation is just showing this. And I think in my many years of teaching this course, so far only one student has taken the trouble to regulate it and show the delta function. So now the question which Dirac asked is, what happens okay, and this is the most interesting part of the story. And so the question is, first thing is, let us consider an electron or any electrically charged particle in a magnetic field. The Hamiltonian, just a free electron, nothing, it would be p minus Ea whole square by 2m. This is the Hamiltonian. And the Schrodinger equation, and let us assume that we are talking about a time independent, just for simplicity, okay, a time independent magnetic field. So this A also is time independent. We assume all these things. So we want to solve H psi equal to some E psi. So the neat observation is that you can actually in some sense get rid of A and write it as an effective, you can make a change if you wish, if you write psi equal to e power let us write something and fix the sign, e integral from, so let me define things properly, psi at some location x, if I define it to be exponential of integral of from some reference point x naught to the point of interest dl, some line integral of a, put an e by h bar, I e by h bar, okay, and let us act on this with p, with the derivative, and ask what you get. So grade times okay. So let us so p acting, the operator p acting on psi is nothing but minus I h bar del acting on psi of x. Okay. So now del acting on this will just pull down. So let me just rewrite that. So p operator is just minus I h bar del operator acting on psi. Some mysterious vector appeared. Okay. So yeah, so this acting on this is actually equal to, so del when it acts on this will have two parts, when it hits this thing and when it hits this one. So I will write them separately. So the first one is when it hits this, what you get? You get A, it will pull down. So there will be an I h bar, which minus I h bar into I, which will cancel this, h bars will cancel. I will get E A times psi, and then there will be a part which would be plus exponential of that line integral from some reference point x naught to x okay. So what this tells you is that I can rewrite this now as p minus E A. Oh, I thought I had to fix the sign, but by some fluke, I mean there is a 50% chance that I would get the right sign. I have got the right sign on psi is nothing but pulling out this phase, let us call this some phase phi, e power I times some phi, I will just define it to be this, is equal to exponential of this I phase times P acting on psi tilde. Okay. A little bit of calculation will show that so what is happening here is you can see when P goes through passes through this exponential phase factor, it gets rid of this A and it is only as if it is a P. So you can write out the Schrodinger equation. So this implies that H psi so I can write some H psi tilde equal to E psi tilde, where H tilde is just as if it were P square upon 2m. So the important point here is that the presence of a vector potential just corresponds to changing the phases of the wave function. Now the question is this phase, we keep saying that the phase of a wave function is not observable, but actually difference of phases is observable. So let us sort of do the following thing. So you can see that this thing depends, has some reference point. So what did we do? We have to, let us say we have x naught is this reference point and x is a point of interest. We can take any different path. Okay, we can go like this. I could have chosen this path, this path. Each of these paths differ by something, differ by the phase. So the answer is actually path dependent. So the phase is path dependent, and let us understand how it is dependent on the path. Okay, so let's choose two paths, gamma 1 and gamma 2, and ask what is the difference of the paths. But so what the phase, so phi of gamma 1 minus, so delta phi will be defined to be phi of gamma 1 minus phi of gamma 2. So but these are both line integrals. So this is an integral over gamma 1 of A dot dl with some factors. What are the factors? I e by, so E by h bar, okay, minus integral over gamma 2 A dot dl. But using a nice property of the integrals, you can see that since as minus gamma 2, I can write this as plus of minus gamma 2, which means just change the orientation of this thing. So this combines to give you a closed loop. Okay, closed loop which is given by the sum of these two A dot dl. But just the same argument shows, going in the opposite direction, shows you that this is equal to the flux through this. The flux through this area. Okay. So clearly this should be observable. So let us sort of so, and you can see that if you are in a region where B is 0, then there is no flux, you would not observe the flux. Okay. So now let us sort of be very, so you can think of a slit experiment where there are no slit, but there is a source of magnetic flux, and we can have a source or whatever, we can have a screen out here. So there can be one path coming like this, another path coming like this, there will be interference. Okay, and clearly the phase difference would be E by h bar times this B dot the flux. Okay, so let us just write this, delta phi is equal to E times the magnetic flux. Okay. So this is just standard non-relativistic quantum mechanics, nothing deep in this stuff. This thing has a name, it is called the Aharonov-Bohm effect. Okay. And this has been observed in the lab, people have seen interference fringes due to these things. Okay. Today I do not know this, I do not know the status in 1931, but definitely today it is known, but I guess okay. So what so now the thing which so Dirac argued, see we have a string out here and this string is not a physical object, it is a given its location is a gauge artifact. So he asked, why, suppose there is a magnetic, suppose there exists one magnetic monopole, that will be a it will have a Dirac string depending on what you chose as your A. And so now the thing is that so the if you want the Dirac string to be unobservable, that would be unobservable only when delta phi would be integrals of multiples of 2 pi, right. Okay. So for a for a Dirac string, the flux is the flux phi due to the monopole of strength G would be G times the 4 pi, because we are talking of the flux, right. It will be G 4 pi, G into 4 pi, and so what we want is, if delta phi is 2 pi n, then the Dirac string is not observable quantum mechanical. Okay. So we can just, we know the flux, so we know what is delta phi, it is E by h bar into phi, which would be G into 4 pi, should be equal to 2 pi over n, 2 pi times some any integer. So what that implies is that E g equal to n h bar by 2. So this sort of is an amazing result. I mean the thing is that Millikan's oil drop experiment told us that the charge was quantized, okay, in units of charge, but we saw that in the standard model there were things which carried 1/3 charge, but for some reason we do not even seem to see 1/3 charges as free things, but okay, but you can say it's things are quantized in terms of 1/3 E, whatever is the number, it does not matter. So what it says is that if you find, if you observe even one particle with G, all the charges in nature should be such that Eg is this thing. So if you are given this G, so E will become, so we can flip this around, I can write it like this, okay, and you can see that all charges in nature, so E could be in this case electron, but I can replace it with some other particle, any other particle, all charges will be quantized in terms of h bar by 2g. So this is the first ever sort of explanation of why charge is quantized, and it is called the Dirac quantization. We will use the English spelling because Dirac was English condition. This is an amazing result, very simple, and we can understand it at a very elementary level, okay. And so actually I would like to read out what Dirac said. Thus the mere existence of one pole of strength G would require all electric charges to be quantized in units of h cross c by 2g, and similarly the existence of one electric charge would require all poles to be quantized, okay. So there should if I have always put c equal to 1, so I am just looking up from here and putting the factor of c out here. So c, I have written capital C here, I mean the speed of light, okay. But coming back to this solution, we know that this looks a little bit sick, in the sense it is not a real, I mean it is not that is not a solution of Maxwell's equations, if you wish, okay, because if you wish there is definitely a singularity at, I mean something which violates the normal Maxwell's equations, but we have already seen in this course that electromagnetism comes from some other thing, it is some SU2 cross U1 broken down to U1. So the underlying theory is something else, at a fundamental level, and the u1 which we see is something else. And so both 't Hooft and Polyakov simultaneously actually ask this question. So suppose we have so the scenario is the following: we have some non-abelian group G and it is broken down to u1 electromagnetism, say. Okay. So now the thing is that so the issue we had was, so let me just draw again. So the issue we had was really at the origin where there is a pole, but suppose we are asking for a classical. So in this thing you look for time independent solution, okay, such that at spatial infinity this is the pattern. So far away, so let me just draw a 2D picture, so that, but it is a 3D picture. So what we have is at the origin we have a problem, but at spatial infinity we are let us say there is a scalar field which gets a wave, there is a Higgs mechanism, and so this non-abelian local symmetry gets broken, and we just have there is only one massless gauge field, and that is a u1. But suppose in this region that is not true, like in the vortex we saw, right, far away the vortex took values where the symmetry was broken, while inside it was restored. Okay. So but so the thing is, so in this region G is broken down to u1, but in this region you could have the full non-abelian, the singularity gets replaced, and what you get is the full non-abelian thing coming back. Okay. So so you can construct such a solution. They looked for a solution of this kind. Okay. So you, when I say that something is charged under magnetism, it is charged under this unbroken u1. Okay. So what they did is constructed, so in the, so the thing is, so let us call this some r naught. So for r greater than r naught, the unbroken symmetry or massless symmetry is u1, okay, and the configuration and A agrees with A for a Dirac monopole. Outside that region, okay, then all your things, whatever you did, you can see that this will give you a magnetic charge, because I can, as long as I choose my sphere to be larger than this, Gauss's law, you can apply standard Gauss's law, and you will, and anyway the charge, so you can think of this as some object lump which is not point like, but has some size r naught and carries magnetic charge, because how would you measure the charge of a finite size object? You would take some Gaussian surface which enclose that surface. So I will do the analog of that, and so this will be magnetically charged, except this is non-singular in this region, there is nothing strange happening. It is just that the web of the scalars etc., which do this, give you end up giving you a nice smooth solution. Okay, so that's what we will discuss in the next lecture. That's also your assignment, and so this is, so here you see here that unlike Dirac's thing, this is truly embedded properly into a nice field theory. There is none, you cannot say the solution is singular and so we can throw it out, nothing. It does not violate the equations of motion, which it did, the Dirac monopole did. It violated at one point, but it violated the equations of motion. Here this will not violate the non-abelian equations of motion, the Euler-Lagrange equations will be it will be a solution. Okay. But for Dirac's argument, I do not think there is any difference between this one, this monopole or that monopole. So the quantization will hold. So, the example we will look at is to take the group to be SO3, okay, and then we will find that there is a solution, and but except I think the quantization of that will not be minimal, it will be 2 times that. It is related to the fact that we saw that SU2 cannot be broken down to U1 by giving in the fundamental. So, you have to take something in the adjoint, which is the same as saying working with SO3 at the level of Lie algebras. Okay. So, this is one we will look at, and so we look at the details of the solution. It is obviously much more hairy, it is not so simple, and it also gives you an example of what we will call soldering of space and gauge indices. Okay. It is a non-trivial example of that, and Etou's paper is I think eminently readable. Polikov's paper I think might be 1 page. So, it has everything, the ideas are there, but much harder to read.